Our solar system is almost uncomfortably vast. Covering these distances using standard chemical propulsion leaves humanity trapped at a frustratingly slow crawl. You have to burn mountains of fuel just to lift the vehicle itself off the ground. By the time you reach orbit, the actual scientific payload you can carry is squeezed into a tiny compartment at the very top. But patience isn't exactly our species' strongest trait, which leads to a wildly tempting question. What if we stopped playing nicely with orbital mechanics and just threw sheer, unapologetic brute force at the problem? We're talking about the ultimate mechanical shortcuts. Ideas like riding the shockwaves of atomic weapons across the void, or physically wrangling the planets together using a massively long rope. These concepts sound exhilarating, and mathematically, they even work on paper. But the moment you try to impose simple force on a complex system, the universe immediately bites back with a cascade of logistical nightmares. Let's start with the nuclear spaceship. The premise of Project Orion was to literally drop atomic bombs out the back of a spacecraft and detonate them. A massive steel pusher plate absorbs that blast, accelerating the ship forward. This chart shows the theoretical jump in performance. Compared to chemical rockets struggling near the bottom, repeating those nuclear blasts thousands of times pushes velocities up to 50 kilometers per second, easily carrying thousands of tons of cargo. At that speed, the solar system shrinks. Instead of a 9-month crawl, a trip to Mars drops to mere weeks or even days. Here is where the logistics break down. To build your deep space nuclear cruiser, you still have to pack those bombs onto standard, highly volatile chemical rockets to get them into orbit in the first place. Rockets explode all the time. An accident on the launch pad wouldn't trigger a nuclear detonation, but the blast would easily rip the payloads apart, showering Earth in radioactive material. And if you somehow survive the launch, you eventually have to stop. Hitting the brakes is a massive engineering hurdle when your only source of deceleration is firing another nuclear weapon in the opposite direction. Well, ultimately, physics didn't kill Project Orion. Proposing a fleet of orbiting nuclear bombs right in the middle of Cold War treaty negotiations was political poison, and the project was scrapped. A mathematically flawless propulsion system falls apart completely the moment it has to survive the messy reality of Earth's atmosphere and human politics. But what if we bypass human politics entirely and manipulate the planets themselves? Imagine we magically line up every planet on one side of the sun and tie them all together with a 4.5 billion kilometer long rope. The first mechanical failure hits instantly. Planets orbit at vastly different speeds. The inner rocky worlds are sprinting around the sun, while the distant gas giants slowly crawl, tearing our neat, straight line apart. Now factor in mass. A behemoth like Jupiter acts as a colossal anchor on the rope. It violently yanks the slower outer planets forward, while dragging the fast inner planets to a dead halt. Orbital momentum is only half the equation. Planets also spin on their own axes, meaning our connection points are constantly in motion. And that spin is completely chaotic. Jupiter rotates rapidly, Uranus rolls sideways, and Venus spins backwards compared to most of its neighbors. Tying the rope directly to the crust means differing rotations will instantly wind your multi-billion kilometer tether into massive planet-sized balls of yarn. You would need planet-scaled bobbins and rotating hooks just to decouple the spin from the tension. Say you engineer those hooks. When the planets inevitably reach opposite sides of their orbits, the center of that tightly pulled rope has to pass directly through the sun. It heats to millions of degrees and vaporizes into plasma. At this macro scale, the sheer kinetic energy of the solar system treats rigid, human-designed structures like tissue paper. Both the nuclear spaceship and the planetary tether teach the exact same lesson. When dealing with the vacuum of space, applying extreme concentrated force guarantees an equally extreme, uncontrollable mechanical reaction. We like problems we can solve by just pushing harder, but celestial mechanics and thermodynamics don't negotiate. They process mass and heat with absolute mathematical indifference. There are still scientists today who look at the vast, empty stretches of the outer solar system and argue we should bring nuclear propulsion back to the drawing board to shorten travel times. But actually establishing a lasting presence out there means respecting the environment. It requires meticulous orbital planning, sustainable materials, and intense patience, rather than relying on explosive shortcuts. We have the imagination to design colossal planetary machinery, and we certainly have the destructive power to try it. But just because we can engineer the absurd doesn't mean we should.